Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will start with the computational mechanics in specifically welding process, and we will specific to the topic the influence of the surface active elements, and we will try to see the other computational methods how to find out that velocity field, temperature field and distortion residual stress that is associated with mainly fusion welding processes. So, we have the theoretical knowledge, or we know about there is a influence of the surface active elements during the welding process, and normally the surface active elements enhance the weld depth of penetration and reduces the weld width if we use the optimum quantity of the surface active elements. But what is the in mathematical point of view, how we can this phenomena represents in true mathematical sense. So, let us see that how it can be done. So, theoretically when we use some surface active elements within the metal or during the welding process. So, here you can see that temperature coefficients of the surface tension is plotted like that, either it can be negative or reaches some optimum point, or maybe it following the negative slope. So, that means in the if you see in the first figure that temperature coefficient of the surface tension, basically over this graph the gradient is greater than 0, that means positive slope reaching towards the optimum point and then gradually decreasing, and then that other way also decreasing, but this generally happens in case of when in presence of surface active elements, for example, that sulfur presence in the steel, that creates this kind of profile of the temperature coefficient of the surface, and other cases when we consider pure element without any surface active elements, they generally flow this negative slope, and that is the representation of the coefficient of the surface coefficients of the surface tensions as a function of the surface active elements. So, let us see that basically this modify the shear stress on the top surface of the oil pool, that means at the interface between the liquid medium and the gaseous medium. So, that shear stress can be represented by this d sigma by dx, that can be represented as a function of temperature, and dt by dx. That means is the temperature, this first one is called temperature coefficients of the surface tension, and this is the temperature gradient. So, by multiplying these two we can represent the what is the shear stress value on the surface. So, that means in presence of surface active elements actually modify the shear stress value considering these two term, either modifying the temperature gradient or either modifying the coefficient of the surface tension. But if we assume that in a specific welding system the temperature gradient is same, but there may be the variation of the coefficients of the surface tension, that can be a function of the surface active elements. For example, here sulfur or maybe some other surface active elements that actually modify this term. That can be either negative or positive, in the sense that if you look into this figure, and this is always temperature gradient is always negative. So, if it is positive or negative depending upon there is a change of the sign, that means shear stress or Marangoni shear stress actually acting depending upon the what sign convention we used for the coefficients of the temperature gradient. For example, if you look into this, it is a pure iron, that means without any surface active elements, the shear stress is basically acting from center to outward periphery. So, direction is given and that shear stress is basically because of that shear stress, the flow pattern normally happens from center to the outward periphery. Maybe we can say that it is the clockwise direction, and but this clockwise direction we follow when this temperature coefficient of surface tension is negative. That means, say for this negative slope, this is the situation. Now, if temperature coefficient of surface tension is positive, then shear stress is basically acting the other direction. So, that Marangoni shear stress is since it is acting towards the center of the oil pool, that actually drive the liquid molten pool from outward periphery to the inward direction. This basically completely reversal of the flow direction happens in presence of the surface active elements. That is, this is the system for the iron, and along with the pure iron, along with the presence of the any surface active elements, and this way it modify the direction of the flow pattern. Here it is looks like that it the metal flow actually happens, or the flow field is in a anti-clockwise direction. So, in the very simplified way to incorporate the effect of the surface active elements in the simulation process, we can use this value, that coefficients of the temperature gradient, this modifying this value, that means whether it is positive or negative, that means whether positive slope and the negative slope, based on that actually impact on the material flow pattern, and we can get either positive or negative value to different flow pattern. One is clockwise direction, another anti-clockwise direction, and of course, we can see that if flow pattern is in this way, that means anti-clockwise direction, that actually enhance the oil pool depth, but it actually reduces the width in other way also. In case of pure iron, that means in absence of any surface active elements, that actually modify the flow pattern in such a way that it actually the low depth of penetration, but width is very high. So, that is the typical impact of the surface active elements, and we can represent mathematically in this way. Now, we will try to see that the heat transfer, in general the heat transfer fluid flow, how it happens in the small oil pool. Here to explain the effect of the surface active elements, experimentally it was observed that in a laser spot welding, there are two picture that actually represents the oil dimension, that means oil width and the oil depth of penetration. And the first case, it has been used that 20 ppm sulfur, I think this is for the material is the high speed steel. So, in high speed steel 20 ppm sulfur we mixed up, presence of 20 ppm sulfur, this actually produce this kind of profile. That means, depth of penetration is not high or aspect ratio is very low, width is very high and depth of penetration is low. But in presence of 150 ppm sulfur, that in for the similar material and the similar welding conditions, that means similar power, laser power and all other laser spot diameter, in all the cases there is a drastic change in the oil pool profile. We can see that here in this case the penetration depth is very high and width is low. Although for the same material, same welding condition, only difference is the one cases is having low amount of the sulfur presence, another cases is the relatively more amount of the sulfur presence in the second case, and that means experimentally it is also observed that there is a tremendous effect of the presence of the surface active elements that actually influence the material flow pattern, and finally, it actually changes the oil pool geometry. So, therefore, it is very important to analyze the significant effect of the surface active elements. Most of the cases we generally neglect or we overlook the presence of the surface active elements in the oil pool. But in computational mechanics point of view, how we can do the simulation, here also we can see that laser spot welding, that similar conditions we have tried to do some simulation, and here we can see the flow pattern. In case of the low sulfur content, this is the profile, and here in this profile we can see that the material flow pattern is in this way. That means and other case, if we see that when there is a presence of the surface active elements, the material flow pattern is in this direction and in this direction. So, in these two cases, although similar welding conditions, but there is a significant difference in the weld pool shape and size because of the presence of the surface active elements within the material itself. But when you try to do the simulation, this material flow, and then we need to consider the positive or negative value of the coefficients of the surface tension that we had discussed, and by changing this value and we can or changing the sign of the coefficients of the surface tension, that actually able to incorporate the effect of the material flow pattern, and finally, will be able to predict the weld pool shape and size in when you do the thermofluid analysis in case of the welding process. But this kind of phenomena not possible to capture when you do the simple heat conduction analysis in welding process. So, here the importance of the material flow consideration in case of the weld pool simulation, that means temperature field as well as fluid flow field in fusion welding process. We have done some experimental also, and we can see that not the earlier case we can see that in case of the laser welding and the surface active elements actually present in the within the material itself. Now, there is other way also in case of TIG welding, but modifying the TIG welding process, that is called activated TIG welding process or tungsten inert gas welding process. So, in this case also normal TIG welding process, this is the surface tension gradient on this, and here if the gradient is like this, that means negative gradient, then flow pattern can be like this, that means material flow from center to outward periphery, and that actually brings the wide depth and low penetration. But other way in a TIG process, so that means activated TIG, that means if by any means if it is possible to add some surface active elements within the base material in the different way, either the surface active elements is already present in the base material, this is the one way, or we can add this active elements by putting some on the surface by putting some coating of the surface active elements, or if it is possible to mix that elements within the shielding gas also, and by these three means it is possible to incorporate the surface active elements to the weld zone, and then there is that called is the activated TIG welding process. So, in that case it simply changes the slope of the surface tension gradient, and that actually brings this kind of profile, that means low width and the high depth of penetration. Let us see that in the first figure, there is one way the surface active elements in TIG welding or gas tungsten arc welding process. So, in this process it is possible to mix the flux powder, and that flux, after mixing this thing with the acetone, mixing with the simply put the coating on the surface, and then if we conduct the welding process, we can find out there is a different profile, although with the for the similar parameters, or maybe if we change the other parameters. So, this is the one way to add the surface active elements within the weld. So, experiments were conducted, you can see that the TiO2, SiO2, Al2O3 all can be used, and then all these three flux are used, actually added and make some coating on these things, and we can find out there is a difference in the weld pool profile. So, here simply that if optimum quantity of surface active elements is added, then actually it creates the from center points to the outward periphery with the presence of the in case presence of Al2O3, but this from center to the outward periphery, when it is happening the liquid metal flow from this direction, that actually indicates that there is no effect of the surface active elements here. That means, it is not necessary all the surface active elements and any quantity actually always enhance the weld penetration and reduces the weld width. Not like that, there is a optimum quantity is required, first thing, and second thing is that surface active elements that for example, Al2O3, TiO2, SiO2. So, all oxides may not act as a surface active elements during the welding process. For example, experimentally observed then in GTAW, gas transient arc welding process, and the surface active flux was used as Al2O3, and we can find out that there is a not increment of the penetration actually. So, width actually increases and for this specific condition, but overall if we see that there is a quantitative comparison of the weld, for example, weld width dimension and the aspect ratio with and without the flux corresponding to that aspect ratio, these two cases is moderately increased, but with the aluminum Al2O3 there is not much increment, that means it is not effective as a surface active elements during the welding process. But if we look into that, there is a TiO2 flux, here you can see, and you can see there is a marginal improvement in the weld penetration, but SiO2 also we can see that also some marginal improvement, that means with reduces and actually depth of penetration increases. So, in this case out of Al2O3, TiO2 and SiO2 or all these fluxes, the TiO2 is the most effective active elements in the present system of the welding, that means with the present conditions of the welding. Now, we can see that also in the other way, that effect of the surface active elements in gas transient arc welding process, but here just I mentioned the surface active elements, that means presence of 4000 ppm oxygen, and that oxygen has been mixed with the shielding gas, that actually acts as a surface active elements, and that actually influence the material flow pattern during the welding process. Here you can see that its a flow pattern is in this direction, that material flow pattern is over, that means there is a effect of the surface active elements, and then we can see that even for the gas transient arc welding process, it possible to achieve the quite high depth of penetration, or that means quite high aspect ratio. So, that means as compared to the laser welding process, this is the other way, that where it is possible to achieve the high depth of penetration just simply using some of the active elements adding to the welding system, that active elements can be added in terms of the flux, and that flux can be put as a coating on the surface, or already the active elements present in the base material, or these active elements can be added with the shielding gas. So, based on that we can find out there is a profile. So, 3 ppm oxygen that actually produce this kind of profile. Of course, the amount of the oxygen presence in this case, that actually decides, not necessary that each this elements is too low, that may not be effective to increase the depth of penetration. Even if it is too high, then that is also not effective to produce the high depth of penetration. So, there is a optimum quantity is required, that optimum quantity actually we can get the optimum value, that means maximum value of the weld penetration in case of the fusion welding process. So, therefore, if we look into that GTA welding process, experiments is generally carried out with the 3 different flux layers, and then we can find out therefore, due to the Marangoni convection of the surface active elements in the weld pool, the weld beam dimension or maybe changes are there may be significant, we can possible to modify, but TiO2 is the most effective as compared to the other surface active elements. But in case of Al2O3, we did not find any kind of this thing effect of the active elements, such that it will produce the high depth of penetration in this case, in all this case. Possibly it needs to optimize the quantity, or maybe it needs to optimize the other process parameters, so that we can get the benefit of the active elements that actually influence the weld dimensions. Now, apart from the surface active elements, and then how the presence of surface active elements actually incorporated in some mathematical model, but just by simplifying or just by modifying the coefficient of the surface tension value, we can incorporate the effect of the surface active elements. But of course, the platform is required to analyze both thermofluid analysis, that means heat transfer as well as the fluid flow analysis, then only we will be able to capture the effect of the surface active elements mathematically. Now, we will try to shift that mechanical model, that means thermomechanical analysis, which is widely used in the welding process. So, here if you see the mechanical model in the fusion welding process, so we can say sometimes thermomechanical modeling. So, of course, in mechanical model is based on the solution of the three governing partial differential equations of the force equilibrium. In tensor notation, it is written that this is the governing equation, that means stress is the body force unit volume, I think, and the stress tensor, they can make the equilibrium conditions, and if we try to solve these cases, we will be able to find out this thing. But of course, the thermomechanical analysis in general, that there is a after doing the thermal analysis, so that temperature distribution actually considered as an input to the mechanical model, and then we try to relate the constitutive relation between the stress and strain or between the strain and displacement. Then we generally predict the distortion field or finally the residual stress field in the welding process, because in fusion welding or maybe other solid state welding processes, it is important to predict at the final distortion level and the residual stress, that is the mostly interested, mostly we generally interest to predict that values. So, of course, when you try to use this governing equation, that means force equilibrium equation, along with that some boundary condition also, that means in terms of the displacement constant, we generally put the boundary condition that depend on the geometry and the body force in the form of the temperature. So, displacement constant in terms of the boundary conditions, and at the same time the body force can be that maybe we can say the load to the thermomechanical model, that can be estimated from the temperature distribution. Here normally we create a geometry and we can define this thing, and within the geometry, depending upon the practical welding condition, we can put the constant, displacement constant, that means somewhere we are putting the clamp, and therefore, we need to put the displacement constant, maybe depending upon the direction, we put the displacement 0 in that specific direction, or maybe on the symmetric surface. Therefore, in the normal to the symmetric surface displacement, we put the displacement constant, and displacement becomes 0. So, therefore, putting the boundary conditions in terms of the displacement and that and then solving the governing equation, assuming the body force from the thermal load, and finally, we solve the displacement field in a thermomechanical analysis, and that displacement, from that displacement field the strain field can be calculated, and of course, from the strain field we can estimate the stress value also. So, if we look into that, how the analysis of the stress and strain is generally done in case of the welding process. Here you can see the temperature history first obtained from the thermal analysis, and that actually acts as input to the structural analysis as a thermal loading. Therefore, each thermal load step and because when we apply the thermal load step, it is not the solution can be done exactly for the one single step. So, therefore, each thermal load step stresses are calculated from the temperature distribution, and normally material model in the sense that assume the follow the von Mises L criteria and the Prandtl flow rule, and of course, some hardening behavior we need to predict, we need to define if we do the thermomechanical analysis. So, normally bilinear isotopic hardening is used, and then in the final form, this is the equation between the stress and strain. So, all the components of the stress and here sigma and all other components represented by strain, and this the D is actually the properties, material properties, and within the elastic limit, if the relate between the stress and strain, therefore, D should be related in the elastic properties of the material, that means in the matrix form, but that elastic property is the Young's modulus and mainly the Poisson's ratio. and then normally we do the analysis assuming the material is the material as an not all elastic. In most of the cases we assume the elastoplastic material. So, when the material is the elastoplastic in nature, then relation between the stress strain can be modified within the elastic limit, the D matrix, the D is you can say the elasticity matrix, or if it is in the plastic zone, then D is can be the D elastoplastic matrix. So, then we need to incorporate the plastic form, what are the material properties we need to incorporate. We will see that how D can be represented in the different way, that means either in elastic analysis or the plastic analysis. But overall stress analysis is done not in a single step, even we consider the bilinear isotropic hardening, that is a linear curve, and it is possible to do the analysis the mostly because elastic component is in linear elastic components. Therefore, the elastic component is represented by the slope, that means it is a linear path. Therefore, in single step it is possible to consider the elastic analysis, but when you enter the plastic stage, then the strain component is divided into smalls in the incremental mode. Basically, each in incremental mode, that means we divide the total strain values in the very small component, that means incremental d epsilon, and that d epsilon consists of the all the three components. So, thermal, maybe if in welding process mainly the thermal load is here, we the thermal strain is generated. So, therefore, this is the thermal strain, incremental mode, plastic strain and the elastic component, elastic strain component. So, that each and every increment we assume this thing, then we update the stress value and the distortion value as well as the strain value in each table. But overall analysis for a long overall duration of the load, we divide into small components, that means small division, small steps of the strain, and then we do the analysis in the incremental mode. That is the basic mode of the analysis. Then it is also important to know that how the displacement or strain is related. So, the displacement and strain field is related by this equation. This is I think linear relation between the strain and the displacement component, but that is called the small displacement theory. That means, in this case normally we neglect the nonlinear term of the distortion, and then we simply relate between the stress and strain by this way. But of course, in some cases when you try to capture the specifically in very thin sheet, when you try to capture the local behavior in the zone, in that case a large displacement theory is necessary to consider. That means, large displacement theory only component is this component, that is nonlinear component of the displacements also need to add, such that we will be able to capture the exactly the deformation behavior in specifically very small thin sheet, and it's which happens in a very localized zone. And that is the either small displacement theory or large displacement theory, we assume that, and then based on that we simply relate between the strain and the displacement. So, one strain has been estimated, and from the strain we can estimate the stress value also. But overall, von Mises criteria, when you try to follow the von Mises yield criteria, then that one effective stress or maybe you can say the average value in one dimensional form can be represented in the all the three principal components, the sigma 1, sigma 2 and sigma 3. All these three components, principal components, can be represented in one dimensional average stress value, that actually follow the von Mises yield criteria, yield functional form. This we also use in case of stress analysis. So, implementation in the finite element method, that means how the stress analysis can be considered in when you try to do some develop using some finite element method. So, definitely first point is that incremental mode, we do the analysis in the incremental mode, that means very small increment of the strain we do the analysis, and incremental stress can be represented like that, d sigma equal to d, and we can find out we say expression for that, and this actually represents the thermal related to the thermal strain, and this when you thermal strain and the elasticity matrix, then we represent that this is the thermal stress value. So, here we can see that incremental stress value is a consist of the three component. This first component is related to the elastic part, this component is the plastic part, and this component is the thermal part. So, here you can see the DE actually represents the elasticity matrix, and this we can see we can represent that DEP, that means elastoplastic matrix, and here this is the this component is the thermal stress value. So, that means the incremental mode, since incremental total strength consists of three components, similarly incremental stress value can be the three components. So, of course, we generally follow the von Mises-Hill criteria and the Pandel-Tools flow rates, but here delta F by delta sigma, that actually consider the deviatoric stress component. So, when you try to estimate the plastic component, we need to consider the deviatoric stress component, and we need to know the tangent modulus, that means local slope of stress versus strain. That actually local in the, if you look into the elastoplastic matrix plastic component, that first component is the linear elastic and then it is a plastic in nature. So, therefore, this part there is a continuous change of the slope. So, we need to consider that at any point at the incremental point, this is the strain value and this is the stress value. So, this is the, suppose this is the incremental point, and here we need to consider the what is the slope, and this slope actually changes. So, the tangent modulus actually changes. So, at any point we need to consider the slope, local stress versus the plastic strain, that slope we need to consider to find out the elastoplastic matrix. And then final matrix in terms of the, so therefore, doing this, then final matrix can be in the in terms of the stiffness matrix K, and D is the incremental nodal displacement vector, and D is the incremental equivalent nodal force due to the thermal stresses, and dB is the incremental external force if any present. So, if there is no external load presence, then it simply becomes 0. That means, we finally we represent the equation in the form of the Ax equal to B in the matrix form, that means in terms of the stiffness matrix, and we solve this stiffness matrix, we will be able to find out the incremental value of the displacement, nodal displacement. So, once we find out the incremental value of the nodal displacement, that displacement field again converted to in terms of the strain component, and then once estimating the strain component, that strain component can be converted to the stress value. So, there in that way we will be able to find out at any point of time, at any stage, what is the value of the displacement, what is the value of the strain, and what is the value of the stress. Or finally, once we know the stress distribution, or if you know the principal stress component sigma 1, sigma 2, sigma 3, then we will be able to find out the von Mises-Hill function, that means average stress value following the von Mises-Hill functional form. So, that all calculations are linked with respect to each other, and we can find out in this way the strain field and strain field simply by predicting the displacement field in case of the simulation. But after doing this, to know some idea about the different types of the distortion, we can see that the transverse sinkage, this is the one type of the distortion we generally follow in welding processes, and we can find out this is the transverse sinkage. So, this actually represents the welding direction, and the transverse sinkage, that means normal to that transverse direction, there is a sinkage of the metals happening, that is called the transverse sinkage. Then longitudinal sinkage. So, with respect to normal to the longitudinal direction, there is a longitudinal section, then there may be angular changes in case of T joint after welding process, and rotational distortion can also be find out in welding process, and then longitudinal bending we can observe after the welding process, and finally, if sheet is very thin, we can mostly we can find out the buckling of this thing. So, these are the different pattern of the distortion generally we observe during the welding process. But how we can predict these things? But here you can see that how we can, that is a serious problem in case welding process, that to eliminate the distortion. Anyway, during the welding process and after finishing the welding process, is considerably changing the phase transformation, microstructural changes also happen, and that happens under the some mechanical constants, all actually responsible to produce the some amount of the distortion and the residuals in the final weld joint. But therefore, it is concerned how to control the distortion in case of the welding process, or how to avoid that. Although it is not possible to completely avoid the distortion, but we can follow proper simple methodology such that distortion can be reduced. So, one is the preset members to counteract distortion. So, before doing the welding process, we can preset the members if we know the which direction distortion will occurs. So, based on that, so if we presetting the members simply to counteract the distortion, that is possible. The second, fixture to clamp workpiece in proper position, we can put the certain fixture in the proper position to avoid any kind of the distortion. Other is the restraint reduces the distortion, but at the same time when you put the some restraints, definitely it will reduce, but at the same time it will try to increase the amount of the residual stress. So, therefore, you should be very careful to apply any kind of the mechanical restraints or to avoid the to reduce the distortion, or that actually increases the residual stress. So, most of the cases after doing the welding process, we generally do the heat treatment such that the properties up to certain extent it can be recovered. That means, we can reduce the distortion, we can reduce the amount of the residual stress. That is the normal procedure to do the heat treatment, simply to recover the certain properties in case of the fusion welding process. But normally, what are the factors that actually affecting the distortion? First is the one factor is the uniformly loading heated and cold, but in welding there is it is a non-uniform heating and non-uniform cooling actually happens in the welding process, that actually creates the distortion. But if you try to create the mostly uniformly heating and the cooling process in case of welding, that actually reduce the amount of the distortion. Second, other factors are the welding locally heats a component. So, one specific component we just locally heat, and therefore, adjacent part is the cold. So, therefore, heat difference in the, or there is a huge temperature gradient exists between the two parts of the component, that actually brings the some amount of the distortion. So, therefore, preheating sometimes helps to actually minimize the distortion. Other factors affecting the distortion is the amount of the restraint, up to what extent the flexible restraint, whether we are using or very rigid restraints we are using, that actually influence the amount of the distortion in case of the welding process. Then welding procedure in the sense that what type of the heat source, what is the typical geometric shape and size, and the material properties that actually used during the welding process, that is also responsible. Then weld joint design, whether butt joint, lap joint, T joint, that actually this thing, and the gap between the two components, all actually influence the influencing factor that actually generate the distortion in case of the welding process. So, therefore, one is the restraint, putting the restraint normally to minimize the distortion. So, therefore, components welded without any external restraints, if you do not put any restraints, are free from to move the distort the in respect of the distort in response to the stress from welding process, that is the one case. Therefore, clamping components, therefore, this restraint does result in the higher residual stress in the components. If you put the clamping components, that actually try to produce the high amount of the residual stress. So, there are in welding process, not only the welding process. So, how we are using the surrounding medium, fixturing not only the fixturing and the material of the fixturing or the high conductive, low conductive material, that actually also influence the amount of the stress, that actually influence the rate of the cooling. So, that finally cooling rate influence the amount of the residual stress generation. But some idea about the measurement of the basic idea measurement of the residual stress, normally we know that non-destructive techniques, normally we use the X-ray diffraction or neutron diffraction. So, both use on the similar kind of the principle, but X-ray diffraction, the limitation is the using the X-ray diffraction method, we can generally measure the residual stress only on the surface. That means, maximum depth of around 0.05 millimeter. So, that means 50 micrometer. This is very less. So, normally you can say on the surface we can using the X-ray diffraction we can measure the residual stress on the surface, but neutron diffraction it can measure the up to certain depth, maybe up to 30 centimeter depth, it is possible to measure the residual stress. But if we want to measure the residual stress using the X-ray diffraction at very high depth, then it is possible to remove the top of the layer. Once we measure the residual stress from top surface, then we need to remove that layer. Then after that we put the similar technology, we put the again X-ray diffraction method follow for the next layer of the surface to measure the residual stress. but neutron diffraction is not, such limitation is not there. It can go up to very high depth of penetration, we can measure the residual stress. So, it follows the Bragg's principle, that lambda equal to 2 d sin theta. Here if you see the theta is a scattering angle and d is the interplanar spacing and lambda is the wavelength of the electromagnetic radiation. So, therefore, the strain is measured by changing in terms of the d. So, delta d by d actually that actually measure the change in the this thing. So, X-ray diffraction is the method to measure the residual stress. Other semi-destructive method and fully destructive techniques that can also be used, the hole drilling method and other is the ring coring, crack compliances, contour method, slitting method, slitting, sectioning method, and of course, these are the other typical type of the semi-destructive residual stress measuring unit, but all actually follow the principle of the strain stress relief. And then of course, this hole drilling method, all this kind of method is we just if we put the using the simple strain gauge, using the very high sensitive strain gauge, if we use it using this, and then it's captured the amount of the strain changes when there is a relief of the stress, and based on that we can measure the amount of the residual stress. These methods are considered the semi-destructive because if the measurements are limited to only one point of the structure, and therefore, that can be repaired very quickly. So, these are the typical methodology for the or basic principle for the measurement of the residual stress. But one important thing is the in analysis or maybe direction of the work in case of the welding process, that is the measurement of the residual stress and how to reduce the residual stress, because residual stress actually impact on the life of the weld joint. Therefore, it is necessary to very important to assess the amount of the residual stress basically generated during the welding process. So, reducing the residual stress, some simple or methodology is that selecting the appropriate processes. Therefore, certain processes we need to select the welding processes, some procedures followed and sequence of the welding and fixturing. If you use the proper way, we can reduce the residual stress generation during the welding process. Selecting the best method for stress relieving and the removing distortion. So, stress relief and the removing distortion we need to consider the best method. Therefore, selecting design detail and the material to minimize the effect of the residual stress. These are the basic principle of to reduce the residual stress, but what are the techniques for the minimize the distortion and residual stress is that welding fixture to physically distant parts, heat sinks to rapidly remove the heat. It is possible to rapidly remove the heat, therefore, we can use the heat sinks also, that actually reduce the distortion, or maybe high conductive fixture material also we can use it, that actually reduce the that actually quickly rapidly remove the heat. Tack welding at we can put the tack at multiple points along the joint to create the rigid structure before the seam welding, that actually minimize the distortion. Preheating the base part, and finally, the stress relief of the heat treatment process, that actually of the weld assembly. This is the most general method to reduce the amount of the distortion and residual stress, simply doing the heat treatment of welding process. Now, we will try to see some distortion field simulation and we can in microplasma welding process. So, here you can see that distortion pattern of 500 micrometer thickness sheet, and here I think in microplasma welding this has been welded, and we try to predict the distortion field. So, here you can see that one cases the distortion is not much flat pattern, other cases it is bending is more in the other cases. So, one cases that means my point is that the of course, irrespective of the magnitude of the maximum distortion amount, the difference, the maximum to minimum is one cases is less, other cases it is very high. So, in the first case it was considered that the small displacement theory, that means when you try to relate between the strain and the displacement, in that case we do not consider the nonlinear component of the displacement. So, in the first case, and the second case we consider the local behavior, that means nonlinear part of the distortion, and that actually predict more precisely the distribution of the distortion in case of the very thin sheet, and that is the in case the second case. So, therefore, in very thin sheet it is we should use the large displacement theory to predict the displacement field. And of course, in the other laser welding process, I think it is a laser welding process. Yes, power 4.5 kilowatt and the speed 41.7 millimeter per second, and spot size is I think not spots 0.63 millimeter. And here you can see using the temperature dependent material properties and bilinear isotopic heating, the first case the residual equivalent displacement. Here we can see the displacement is maximum at the which point the heat source will move at the edge, along the edge, and the second case also residual equivalent strain amount also generated more or less that along the weld line. So, this way it is possible to predict through the finite element based numerical model the amount of the residual equivalent displacement and also residual equivalent strain. That means, single value of the displacement and single value of the strain. Here you can see the maximum strain amount is as if around 0.156, and residual displacement we can find out that around I think 0.3 millimeter. Similarly, in the laser spot welding also we can find out the for 1 kilowatt laser spot welding, this is the simulation of the residual distortion. So, in the first case the if on time is 0.15 second result is on, then we can find out the distortion, residual distortion is very small and it is confined into the very small area. But once the is increases, that means laser on time is increases up to 0.65 second, then we can find out that residual distortion, the area actually increasing through which the residual distortion we can observe. And of course, in these cases that one case is the residual stress and the equivalent plastic strain. In the two cases, one is the at 0.15 second 1 kilowatt laser, we can see the residual stress is basically confined as a small area near about the weld spot. In other cases, we can equivalent plastic strain also confined, it is a very small area. We can see other also that thermomechanical analysis of the micro laser spot welding process. So, that material SS304 stainless steel here, and 2 laser power 25 watt and 75 watt has been used, and laser type continuous wave fiber and thickness is only 100 micrometer. So, in this case we can see in the residual displacement is actually confined, it is a very small, it is a spot welding, it is a very small zone, but if we zoom it we can see that this is the displacement of the residual stress here in the thing, and here you can see the two different I think here is the two different cases. Similarly, equivalent residual stress we can find out that this is the distribution. Normally, the residual stress distributed over a bigger zone as compared to the residual displacement. So, here you can see that first figure the residual stress distribution, and the second is the equivalent plastic strain. Plastic strain is basically confined, it is very small area, and of course, the maximum value is towards the bottom side of this thing, because it actually depends the sheet thickness, and that because normally thickness direction the temperature gradient is less, and of course, at the same time what is the amount of the heat loss from the bottom surface. That means, whether we using any kind of high conductive material from the bottom side, based on that the location of the equivalent strain or residual strain maximum amount will vary depending upon that. So, this just want to see that here you can see that what way that residual stress is distributed in case of the welding process. So, that of course, this residual stress has been calculated once after putting the heat input, and then when you heat input is not in this way, that means after solidification happens and when it comes back to the room temperature, then this is the permanent amount of the stress, strain or distortion field is actually generated in the welding process. These are the typical distribution. So, stress relieving of weld, some significant points that related to the residual stress and distortion in welding process, that preheating actually reduces the problem. So, before welding process, if we preheat the sample, that actually reduces the problem caused by the during the welding process. Second is the heating can be done, but this preheating can be done electrically in the furnace for the thin surface radiant lamp or maybe hot air blast. So, therefore, there are several ways to actually practically do the preheating, because preheating sometimes reduces the amount of the problem related to the welding process. Then some other methods of stress relieving, that means pinning, hammering, surface rolling, these are the other mechanical methods that actually remove the amount of the residual stress in the welding process. So, in summary, for the whole the computational methods in case of the welding processes, we can see that first we have described the different heat source model depending on the type of the welding process, because heat source model is significant if we try to correctly predict the amount of the distortion and residual stress. So, in that sense, correct representation of the heat source is important in the welding simulation. So, therefore, and that representation of heat source actually depends on the two points. One is the geometric shape of the heat source, and second point is the distribution. So, based on that, different type of the heat source models has been developed to represent the different welding processes. Next was estimation of the temperature distribution in the weld zone and the heat affected zone by solving the heat conduction. So, we have discussed using the temperature distribution can be done by simply solving the heat conduction equation with the proper boundary conditions. Of course, incorporation of the fluid flow enhance the, that means more precision results of temperature distribution and the fluid flow, material flow is better represented if we consider the material fluid flow in case of the welding process as compared to the only the heat conduction analysis. And of course, surface active elements presence of the or effect of the surface active elements is better represented or better explained by incorporating the fluid flow phenomena in the oil pool simulation. And but point is that coupled thermofluid analysis is definitely computationally very expensive. So, most of the cases we neglect the fluid flow analysis and we do only the heat conduction analysis. Then mechanical analysis predicts the distortion and the residual stress, but mechanical analysis needs to be considered the temperature distribution as an input to predict the distortion residual stress in case of the welding process. Then of course, coupled thermomechanical analysis again is also computationally very expensive. And then cooling rate, we can from this numerical model or data if we know the temperature distribution. So, from that temperature distribution we can estimate the cooling rate, and that cooling rate can be linked with the microstructure in a welded structure. So, therefore, just simply calculating the cooling rate, it is possible to predict the what are the microstructure presence in the welded joint. Then of course, simulation is important or significant when there is a difficulty of doing or to capture the phenomena simply by doing the experiments, because it is not possible to capture all the phenomena that happens during the welding process experimentally. So, here there is a need of the numerical simulation. For example, the experimental evidence of the material flow within the oil pool is very difficult to do experimentally. So, therefore, numerical simulation can be a recourse to better understanding of this phenomenological behavior in case of the oil pool simulation. So, with this, so thank you very much for your kind attention.